Hello, everyone, and welcome to the 100th webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's webinar will consist of a brief overview of the two programs, followed by a technical portion, which details results from Department of Defense funded research on aqueous film-forming foams, or AFFF. First, Dr. Michelle Crimi from Clarkson University will discuss the state of knowledge regarding the treatment of groundwater impacted by AFFF. Her presentation will be followed by a question and answer session. Second, Mr. Jerry Back from Jensen Hughes will discuss the results from a 2-year effort to assess the capabilities of environmentally friendly AFFF alternatives, including both traditional candidates such as fluorine-free foams and non-traditional options such as wetting agents and other water additives. His presentation will also be followed by a Q&A session, and as time permits, we will conclude the webinar with a final Q&A session with both of today's speakers. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use. If you lose the content on your screen, or if your screen freezes, try keying Control F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience technical difficulties, please feel free to call into the conference line shown on this slide. You can also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties, because the Q&A option should be reserved for questions for our two speakers. Today's broadcast will be listen only. We have over 600 folks on the line. So you may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions as you come up with them well in advance of the Q&A sessions. When you submit your questions, please make sure to add your organization name at the end of your question so that we can identify you. With that, I would like to introduce Mr. Timothy Tatro, who's the ESTCP Program Manager for Energy and Water. Tim kindly agreed to provide SERDP and ESTCP introductory remarks on behalf of Drs. Andrea Leeson and Robin Nisan, who are not able to join us today. And they are the program area managers for both environmental restoration and weapon systems and platforms. Before joining SERDP and ESTCP, Tim worked at the National Renewable Energy Lab, where his work focused on energy efficiency and renewable energy project development for the federal sector. Tim? Tim, can you please proceed? I will just give Tim a moment in case he's experiencing issues with the audio. Tim, let me know when you're on the line, please. All right, in the absence of Tim being able to join, I'll go ahead and introduce the SERDP and ESTCP program areas. On slide number 9, this is a quick overview of SERDP, which is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress as a partnership between the DoD, the DOE, and EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. On slide number 10, we introduce ESTCP. For those of you that are not familiar with the program, ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments typically capitalize on past investments under SERDP or other research programs, and they are specifically designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is that ultimate transition to both implementation and regulatory acceptance. Please note that SERDP and ESTCP are complementary programs, with much of SERDP research occurring either at the lab or pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts, specifically treatability studies, are conducted. On slide number 11, we show the 5 program areas within the SERDP and ESTCP programs. There are 4 program areas in SERDP and 5 in ESTCP. The installation, energy, and water program is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapons systems and platforms are SERDP and ESTCP programs managed jointly by a designated program manager. Today's webinar on slide number 12 presents results from research and demonstration efforts that were conducted under 2 program areas, environmental restoration and weapons systems and platforms. Environmental restoration has 5 main areas of research. Those include contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Weapons systems and platforms on slide number 13 also has 5 major areas of research. Those include surface engineering and structural materials, energetic materials and munitions, noise and emissions, waste reduction and treatment in DoD operations, and lead-free electronics. On slide number 14, you can see that our webinar series highlights research and demonstration efforts from each of the 5 program areas. Upcoming webinars will cover a broad range of topics. You'll see an ER webinar coming up next week on high-resolution site characterization. On October 31st, we'll have a weapons systems and platforms webinar on sustainable coating systems for military platforms. On November 7th, we'll have another PFAS-related webinar on SERDP and ESTCP efforts on developing and demonstrating PFAS treatment technologies. And we'll conclude the 2019 webinar series with another ER webinar in December on monitoring and treating groundwater contaminated with chlorinated solvents. On slide 15, you can find additional information about upcoming webinars at this link. Note that registration is live for webinars through the end of this year, and we'll be releasing the 2020 calendar shortly. I'd like to remind you that a copy of the presentation of today's session can be downloaded from this webinar webpage. Towards the end of the webinar, please stay tuned because we would really appreciate it if you could take a moment to complete a short survey that will pop up on your screen and that will help inform future webinars. I'm pleased to announce that the SERDP and ESTCP Symposium will be held again this coming December in Washington, D.C. This 3-day event will showcase the latest technologies that enhance DoD's mission through environmental and improved environmental and energy performance. Registration information is available on the SERDP and ESTCP website. At this point, I would like to introduce our first technical speaker, Dr. Michelle Kearney, who is a professor at Clarkson University in Potsdam, New York. Michelle has been at Clarkson for 11 years, and before that, she served as an assistant professor at East Tennessee State University and a research assistant professor at the Colorado School of Mines. Michelle's research focuses on developing in situ treatment technologies for groundwater remediation, determining the impact of groundwater technologies on aquifer quality, and integrating treatment technologies for optimized risk reduction. Michelle received her doctorate in environmental science and engineering from the Colorado School of Mines, her master's degree in environmental health from Colorado State University, and her bachelor's degree in industrial hygiene and environmental toxicology from Clarkson. Michelle, please proceed.
Thank you so much, Rula. I just want to confirm quickly that you can hear me okay on the line?
Yes.
Great. So today I'll be covering some of the basics regarding treatment of PFAS-contaminated groundwater. The goals are to discuss why treating PFAS is particularly difficult, to describe some of the remediation approaches that are available or coming down the pipeline, focusing on carbon-based sorption, ion exchange, and some examples of aggressive destructive treatment options. To introduce some of the key considerations in selecting a remedy for treating PFAS-contaminated groundwater, and to wrap up with benefits to DOD. Treating PFAS is particularly challenging relative to the treatment of more traditional contaminants for several reasons. First, the chemical properties of PFAS make them tricky. The carbon-fluorine bond is one of the strongest bonds in nature and requires significant energy to break. Also, PFAS are surface active because of their hydrophilic heads and hydrophobic tails, so their partitioning and behavior are difficult to predict. They're also very soluble and don't transfer as easily to air or solid surfaces as many contaminants that we're used to working with. Also, target PFAS are typically present amongst a suite of contaminants at a site, whether with many of the over 3,000 other PFAS compounds or present with other types of co-contaminants. The broad suite of PFAS compounds also contain highly varied properties, so an approach that is good for one compound or group of PFAS compounds may not be particularly effective for others. Finally, precursors are a challenge to treatment. Precursors are some of the larger chain PFAS compounds that are typically present at AFFF and other PFAS contaminated sites. They're partially degradable and they can break down into some of the same compounds that we're targeting to treat. Additionally, most treatment processes will be affected by the presence and concentration of precursors. And this is difficult to manage, particularly because many can't even be identified or quantified with current standard analytical approaches because of the lack of available reference standards. We have three big picture options to treat PFAS-contaminated groundwater. We can immobilize them in the subsurface, typically using sorptive amendments. We can separate them from source water using processes like sorption and membrane separation as examples, or we can destroy them, ideally generating innocuous byproducts. Currently, off-site incineration is the most common and readily available destructive approach. However, several other options are under development, many of which may be implementable on site, which would help to minimize liability and transportation costs. A favorable approach to manage PFAS-contaminated groundwater is a combined remedy, where separation processes are used to concentrate PFAS, and the concentrate is then destroyed. In this approach, the limitations of one are overcome by the advantages of the other toward improved efficiency of treatment. Looking at examples of these options in a bit more detail, separation can be achieved by filtration, coagulation, sorption, and ion exchange. Sorption using granular activated carbon, or GAC, and ion exchange using both single-use and regenerable resins are currently the most common. However, new developments are increasing the feasibility and decreasing the cost of filtration and coagulation approaches. There are an array of destructive approaches, most of which are currently under development, including oxidation, reduction, electro and photochemical, sonolytic, and plasma treatment. Most of these are energy demanding, so there is indeed significant value in a pre-treatment concentration step as a treatment train or a combined remedy. The SERDP ESTCP program has funded numerous projects focused on treating PFAS in water and in investigation-derived waste. Several are listed here just as examples. Note some of the key words underlined: sorption, ion exchange, electrochemical oxidation, integrated approaches, treatment train. The goal is to develop approaches that are not only effective at treating PFAS, but to do so with the greatest efficiency, as we know that this is a large-scale and extensive problem. I think our future holds an array of options to choose from, ultimately based on site-specific factors and cost implications. I'm going to go through a few examples and considerations for some of the key approaches that we currently have available, as well as some example approaches coming down the pipeline. So as I mentioned, treatment using activated carbon is currently most common. Carbon-based treatment systems are versatile. They're implementable for both large and small-scale systems, as well as both in situ and ex situ. There are an array of carbon sources out there, and new blends, as well as synthetic media, are under testing and development toward improving sorption capacity. Not all carbon behaves the same under the wide range of contaminant, co-contaminant, and geochemical conditions of different sites. Therefore, treatability testing with site-specific groundwater and the specific carbon to be used on site is very important. Additionally, not all PFAS compounds behave the same. Shorter chain compounds are more difficult to remove by separation than larger chain compounds, for example. Sorption behavior for PFAS is less predictable overall than it is for other types of contaminants. For example, one challenge is the fact that PFAS compounds can form micelles and hemimicelles even at concentrations well below their critical micelle concentration. Sometimes this can aid and enhance sorption, while other times it can inhibit it, depending on the carbon properties. Excuse me. Many researchers are working on improved understanding and prediction of the sorption and fate of the broad suite of PFAS compounds. It's possible for GAC to be reused. The GAC can be shipped back to the vendor and reactivated by heating it to 1300 degrees Fahrenheit. This same GAC is then returned to the customer for reuse. Many researchers and practitioners are also working on alternative on-site approaches to regenerate GAC for its reuse. Ion exchange is a separation approach that offers an alternative to carbon. As you see in this example provided by my colleagues at Wood and ECT2, effective single-use and regenerable resins have been identified. In this figure, the blue bar represents PFAS mass delivered to 3 different ion exchange resins, A, B, and C. The green bar indicates mass removed by resins, with B and C proving particularly effective. Resin C, however, is also regenerable, with the red bar showing the PFAS mass recovered from the resin. This recovered mass, now concentrated in a much smaller volume, becomes more efficient to destroy. Here you see a comparison of PFAS removal by one ion exchange resin, shown in green, to that of one type of carbon, shown in gray. In this example, the resin outperforms the GAC with significantly more volume of water treated before breakthrough with the resin for key larger chain compounds like the 2 that you see outlined in blue towards the right. However, ion exchange resins, like carbon, are challenged by some of the smaller chain compounds. Here you see outlined in red toward the left an example of the significantly lower volume of water treated before breakthrough by both resin and GAC compared to other larger compounds. The majority of technologies that I mentioned at the beginning of the presentation that destroy PFAS compounds actually do so by manipulating redox conditions in a very aggressive way. For example, plasma treatment uses electricity to convert water into a mixture of highly reactive species. A key one of these being aqueous electrons, which are very aggressive reactants capable of destroying even the most recalcitrant PFAS compounds. My colleagues at Clarkson have designed, built, and tested a plasma treatment system, different scales of which you see here in the photos, with the one on the farthest right being a deployable field scale unit. My colleagues Tom Holson and Salma Medetovic and their research group have treated a broad range of contaminated site groundwater samples using their plasma treatment system. Here you see the range of conditions for 13 different site samples, most of these conditions spanning several orders of magnitude across the 13 samples, including their initial PFAS concentrations, which are shown toward the bottom of the table, the sum of acids, the sum of sulfonates, the individual alkyl acids, and as total fluorine. Here, you see the removal efficiency summarized for these samples with an applied treatment time of 1 hour or less with their system. We see greater than 90% removal across the board for the key long-chain PFAS compounds and several of the precursor compounds. Treatment of longer-chain precursors and compounds progresses through shorter-chain precursors and compounds. So you see the generation of these as reaction intermediates in some of the samples, but these too are treated under longer treatment durations. Another approach we're working on at Clarkson is an in situ sonolytic treatment approach. We've developed a reactor that gets emplaced within a horizontal well in the subsurface. Horizontal wells passively capture water. As the path of least resistance for water to flow, a well that is less than 1 foot in diameter can capture water in a treatment zone of up to 50 feet or more, requiring no pumping at all. The idea is that water flows into the reactor, is treated, and then clean water exits the well. We've tested this reactor in the laboratory using contaminated site groundwater with results shown here. Each color represents a different site. Results for PFOA, one target contaminant, are shown by the left-hand bar for each color. And results for PFAS, another target contaminant, are shown by the right-hand bar for each color. The number above the bar shows the applied treatment time in minutes. And the initial PFAS concentration for each site is shown below the graph just as one point of reference. While treatment effectiveness varies as a function of site conditions, effective treatment is achievable given a long enough treatment time. The key site parameter impacting treatment time is actually not the target compound concentration, but is the concentration of precursors that are also present in the water. This sonolytic treatment process also proceeds through shorter chain intermediates, the generation of which you see here. PFBA, the bars on the left for each color, and PFBS, the bars on the right, are two short 4-carbon compounds. Their production and ultimate removal also depend on the initial precursor load. Because of their generation as intermediates, we wanted to confirm treatment of these smaller chain compounds, that they're being destroyed even while being generated as intermediates. The example for treatment of PFBA, one of the hardest to treat compounds, is shown here. So we do indeed treat these smaller chain compounds in this sonolytic system. Plasma and Sonolysis are just a couple of the destructive treatment approaches under development. Others include electrochemical, photochemical, reductive, and oxidative approaches. These are described in more detail in the reference that you see shown at the bottom of the slide, and they'll also be summarized in the upcoming ITRC guidance document soon to come out. If it hasn't been emphasized enough in the examples I showed so far, I really want to stress the importance of showing complete destruction of PFAS using destructive technologies. The literature points to many examples of reaction intermediates and byproducts that have been measured in studies using the technologies listed here in this overwhelming table of acronyms. Just because your target compounds like PFOA and PFAS may be disappearing doesn't necessarily mean you have complete destruction. It's important to look for potential byproducts and to confirm the fate of your target compounds. It's helpful to measure the increases and decreases in reaction intermediates over time. We wouldn't want to write off technologies that generate reaction intermediates that do continue to degrade over time by assuming that these are ultimate byproducts. I've mentioned the value of treatment trains a couple of times. One example I want to highlight is a SERDP project that we at Clarkson are working on with our colleagues at Texas Tech, ECT2, and Wood. We're using traditional oxidative approaches to evaluate precursor transformation in situ with the goal of reducing or eliminating them as a long-term source of PFAS compounds of concern. This is shown here as Part A, in situ treatment. Part A is followed by Part B, pump and treat using a regenerable ion exchange resin. Our goal is to not only reuse the resin, but also to reuse the solution used to regenerate the resin. Once separated, the concentrated waste stream is then treated by plasma. This is a fully on-site process that results in almost no post-treatment waste stream to manage. For Part A in situ, we'll be testing 3 different oxidative approaches for precursor treatment: for sulfate oxidation, oxygen sparging, and slow release oxygen. For Part B, ion exchange, we're evaluating the effectiveness of different regenerant solutions in pulling PFAS back off of the resin. We're also testing several approaches to separate the PFAS from the regenerant solution so that it can be reused. For the plasma treatment component, we're comparing the efficiency of treating straight contaminated groundwater to that for the concentrated ion exchange residue and also the pre-treated oxidized groundwater. The ultimate goal is to couple the most efficient components of this integrated treatment process and assess what the technical and cost challenges may be at full scale. So, summarizing the challenges and limitations of PFAS treatment, PFAS are hard to treat because they're present in mixtures and because precursors impact treatment efficiency and can turn into our target compounds. Many current treatment processes ultimately result in a materials waste stream, such as GAC or single-use resin treatment, which then must be managed as a hazardous waste. For destructive approaches, incomplete mineralization must be avoided, and we need to identify and advance lower energy treatment systems. Also, we need more examples of field-scale implementation of both in situ and ex situ approaches. When selecting potential treatment options for a site, there are a few key considerations. Does the approach rely on immobilization? And if so, to what extent can immobilization be verified to be irreversible? Does the approach rely on separation? If so, how will the separated PFAS be managed? What are the implications of this management plan? Can removal efficiency be improved at a reasonable cost? Does the approach rely on destruction? If so, can this be verified through analyses? Are intermediates or byproducts generated during treatment? How do precursors affect treatment? And what are the cost and implementation challenges? The DoD estimates PFAS-related liabilities on the order of $2 billion or more. As regulations emerge and evolve, it's becoming more clear that there's a need for effective, cost-effective PFAS treatment approaches. Many in the research and practitioner community are working on developing and improving such treatment approaches, and I think we'll see our options continue to evolve. Thank you so much for your time and attention.
Great. Thank you so much, Michelle, for a great overview of the state of knowledge regarding treatment and some of the innovative technologies that are being developed. We have a number of questions that have come in for you. As a reminder for our audience, you submit your questions by using the Q&A box on your screen. All right, so Michelle, this is a question from the American Waterworks Association. How do ion exchange resins compare with granule activated carbon for capturing not just a few PFAS, but PFAS mixtures?
So it really depends on what's in that mixture and the characteristics of the specific resin. So while I'm not actually trying to avoid the question, there's really not a straightforward answer to that. It really depends on the specific constituents. And what I always recommend is a treatability test with the specific water of concern to make that comparison, to make that a quantitative comparison.
Great, thank you, Michelle. This is a question from EPA. You stated that micelles may form even below critical micelle concentrations. Why is that? And can you provide a few references for detailed information on the phenomena?
Yes, so my suggestion is that you email me. I don't have those references handy with me right now, but if whoever asked that question sends me an email, I would be more than happy to send some examples. And it's really the way they start to line up within the pores of the GAC, so it depends on the surface properties of the GAC and how the individual molecules start to align within those pores. So I don't want to spend a lot of time going into detail on that phenomenon, but like I said, I'd be really happy to answer that in more detail by email or a phone call.
Great, thank you, Michelle. And if we can just go back one slide, Michelle's email address is available on the screen. You can also download a copy of the slides of the PDF from the SERDP ESTCP website. And you could visit the link that is shown on the slide to go to Michelle's project webpage, which also includes her contact information. All right, an additional question for you, Michelle. How do co-contaminants impact destructive treatment of PFAS? So you're working in deionized water systems. When you start working with field samples that contain identified or non-identified co-contaminants, how do you expect treatment efficiency to change?
So that is a really good question. So my colleagues who have the plasma treatment system, they've looked quite extensively at this, and the presence of co-contaminants do not impact the efficiency of plasma treatment. And then sonolytic treatment, we have treated site groundwater, and while we haven't measured the specific co-contaminants, we do measure that precursor load in the system. So other PFAS that are present that aren't being quantified by the standard analytical methods do impact the efficiency of treatment, but not the overall effectiveness. In other words, it will take longer to treat when there are PFAS-related co-contaminants there. With these very aggressive, destructive approaches, more broadly speaking, most of them will readily treat the more common contaminants that you would find on a site. As I mentioned, they're really aggressive, and they tend to break down most of what you would find in these groundwater systems.
Great, thank you, Michelle. This is another question from TriHydro. You talked about granule activated carbon and ion exchange for and their limitations with potentially the shorter chain PFAS. What about nanofiltration or reverse osmosis? Could those be more effective for the shorter chain PFAS?
I don't know the answer to that off the top of my head, and I would hate to say something incorrect. So that is a question I would be happy to address offline. I know I have that information, just not handy with me right now, so I don't want to misspeak on that question.
All right, so they'll follow up with you by email. A question from Doyon Utilities. What is the cost to scale these treatment technologies either separately or in treatment frames? Are they ready for full-scale applications? And is it an economical proposition at this stage? Michelle?
Yeah, those are great questions. So, so the separation approaches of carbon and the ion exchange systems, those are in common use right now. And, you know, I don't have cost comparison data at my fingertips, but those are used in the field already, and I know that information is available, especially from the vendors of those technologies. My colleague's plasma treatment system, they have field tested that system, and so that one is ready. I don't have the cost comparison info at my fingertips. I do know that their analyses show it to be a cost-effective solution. For the sonolytic treatments, we have not field demonstrated that technology yet, so we've done some rough estimates. Implementation costs, startup costs would be similar to, say, a pump and treat system, but operational costs would be less based on our estimates because you don't have the material change out and management costs.
Great, thank you, Michelle. A question from the U.S. Naval Research Lab, and if we could please go to slide 32. So for the data in this slide, can you provide a reference if the information has been published, or can we contact you, Michelle, for additional information specific to the plasma work on slide 32?
Yes, this is a recent publication by my colleagues. I don't have that at my fingertips right now, but I would be more than happy to provide you with that information if you send me an email or give me a call.
Great, thank you. And maybe one last question before we transition to the next speaker, and not to worry, we will get back to Michelle in the final Q&A. We're doing really well on time. With regards to, you mentioned that you would recommend activated, if you're trying to make a decision, Michelle, between activated carbon or ion exchange resins to treat PFAS, that you recommend treatability studies with site-specific media from the contaminated site. Do you have any experience, and can you speak to how frequently one must, how frequently carbon or ion exchange resins must be changed out, especially compared to treatment systems that are treating conventional contaminants versus PFAS?
Yeah, that's a really good question. It is a very site-specific answer. And that, you know, that is the primary purpose of doing the treatability tests. What I'm hearing is, you know, a year, but I've also heard less than that. I've also heard longer than that. So I think it can vary. I think it's generally speaking more rapid change out than a lot of contaminants, because PFAS tend to be less sorptive than other contaminants. So I do think the change out is more frequent than what we may be used to with traditional contaminants.
Great, thank you. And one last question that just came in from the University of Maryland. For your plasma work, what is the concentration range that you are working with? to treat concentrated water after separation. I think you have the percent removal, but you don't mention the initial concentration. Can you speak to that, Michelle?
Yeah, so the percent removal shown in the slides was for straight groundwater, not the concentrated residue. We are working on treating concentrated residue, and those concentrations can be in the milligram per liter range plus.
Great, thank you, Michelle. And it is now time to transition to our second speaker today. We're delighted to have Mr. Jerry Bach, who is a senior fire protection engineer with Jensen Hughes, Baltimore, Maryland. Jerry was one of the original Hughes Associates employees and has over 35 years of experience in fire protection topics and issues. Jerry has performed thousands of full-scale fire tests, including evaluations of AFFF agents and systems, aerosols, high expansion foam systems, gaseous agents, water mist systems, and water spray dilute systems. These full-scale fire tests were performed on behalf of the Air Force, Army, Coast Guard, Navy, the Federal Aviation Administration, as well as commercial clients. Jerry's academic background includes a bachelor's degree in mechanical engineering and a master's degree in fire protection engineering, both from the University of Maryland. Jerry, we're delighted to have you. Please proceed.
Thank you very much, Rola. Let me verify that you can hear me. Can you hear me okay?
Great. Go ahead.
Okay. So everyone, the presentation is basically going to be an introduction of the 2-year program that we have initiated back in the spring to take a look at the capabilities of commercially available firefighting capabilities of the commercially available fluorine-free firefighting foams and agents as a potential replacement for AFFF, which is the 50-year industry standard used to combat flammable liquid pool fires and fires along those lines. The full-blown data set won't be available for about a year because we just started the program in the spring, but we will try to keep you posted on the website as we go through and we actually collect some of the data. So as far as what's covered in the presentation, I'll give you a quick background of AFFF and how it's been used and the problem associated with its use and the concerns today, our program objectives, our approach to assessing the capabilities of these potential alternatives, and it includes 6 tasks. The benefit for DoD from doing the research, the status where we are today and the schedule for completion, and then some conclusions and some summaries of what we found so far to date. As far as the background, as I mentioned earlier, AFFF has been the industry standard for combating flammable liquid pool fires for over 50 years. It was invented by the Naval Research Lab back in the late 60s, early 70s, and it eventually evolved after it was being refined into a mil-spec, mil-F-24385, which is still the mil-spec today. It's a mil-perf now. But foams are still being approved to that today, AFFFs are. The development of AFFF was driven by a couple catastrophic events, and the most notable being the fire that occurred on the USS Forrestal in 1967. And during that event, a rocket accidentally fired and hit another plane on the flight deck of an aircraft carrier and caused a large spill pool fire underneath of the plane. And the plane was loaded with live ordnance. The damage control party at the ship immediately responded to the event. They grabbed their firefighting gear and they went running into the fire to put the fire out. Within about 90 seconds into the event, the first bomb on the plane exploded, killing most of the damage control folks and firefighters on the ship in one quick event. If you wanted to watch a heartbreaking video, go to YouTube and see this. But needless to say, it got worse from there. In total, 134 sailors died, 161 were injured. But the takeaway from the event was the DoD needed an agent that could rapidly extinguish flammable liquid fires to prevent ordnance cook-off in a scenario like this. And that basically set the bar for the mil-spec foams as being fires needed to be extinguished in less than a minute to prevent this ordnance cook-off. And that requirement's probably the most strict out of all the approval tests today. And as a result, the mil-spec approved foams have always been the best performer because they've been tested to higher standards than other industries are testing foams in general. As far as just general use AFFF, besides DOD, it's used in the aviation industry and in the commercial industry. From a shipboard's perspective for the DOD, it's used on the flight decks of aircraft carriers, which I just showed you, bilges, flammable liquid storerooms and flammable pump rooms, aircraft hangars, and for manual firefighting. For aviation, land-based aircraft hangars, ARF, aircraft rescue and firefighting vehicles. And over the years, the FAA has always defaulted to using mil-spec foam because their opinion was the burn through of the fuselage occurs in about a minute or so, so they needed very fast extinguishment times too. But as of recently, they're now allowing the use of ICAO, International Civil Aviation Organization, approvals to approve foams for land-based commercial airfields. The petroleum industry uses it in refineries, fuel stations, and tank farms. So as Michelle kind of alluded to in her presentation, there are a number of concerns with the use of AFFF groundwater contamination, and it's both an environmental and a health concern, and that the regulatory landscape is changing on a daily basis. So DOD needs to identify or develop an environmentally acceptable alternative to AFFF with the understanding that with these regulations changing, that the use of AFFF is going to be limited in the future and maybe even potentially banned, but we'll see. But I wanted to make a point that we need to be careful about doing the replacement of AFFF because the use of a firefighting agent in general is a life safety issue. So we need to make sure we don't compromise performance too much in the process of trying to address some of these other concerns. So the ultimate objective of our program is to identify an environmentally acceptable alternative. That's the ultimate objective. So I think we're going to get there. I doubt it on this particular test program, but we'll definitely be well on our way. But in general, being able to quantify the capabilities of the available alternatives, the state of the art, as you would say, today, and start a database on that is a very good first step in trying to understand what the next step would be if indeed AFFF becomes, limited use throughout the industry. As far as kind of the maturity of environmentally friendly / fluorine-free foams, there are numerous commercially available fluorine-free foams out there today. They're approved to UL 162, a British standard EN 1568, I believe the number is, and ICAO, the International Civil Aviation Organization. And that, so in some respects, they're ahead of the DOD as far as getting foams out there. In our assessment, we're looking at those foams as well as other agents like wetting agents and encapsulating agents that have been shown to do reasonably well against flammable liquid pool fires. And we're even thinking outside of the box as far as other chemicals like the types of chemicals that are used to suppress grease fires in kitchens, even stuff like de-icing chemicals like aqueous potassium acetate, things like that as an additive, with the idea that nothing's off the table at this point. Let's just see how we can do as far as capabilities of all of those potential candidates. So our approach consists of 6 tasks: a literature search, an environmental analysis to kind of down select agents for testing. We're going to start with real scale fire testing. Then we're going to rank the capabilities of the real scale testing. And then we're going to go back to approval scale tests to see how they do. And then ultimately we're going to document the entire program in an all-encompassing final report and with a lot of lessons learned and recommendations for the future. And we're going to bring in a lot of end user, subject matter expert types to kind of weigh in on helping us assess what we believe the capabilities of these are. But so as an interesting point, I wanted to emphasize that we're running real scale fire tests before we're actually running the approval scale fire tests. And that's how AFFF was invented way back in the day, 50 some years ago, that the tests were all done on real scales before the development of the small scale test. And there's so much focus now on getting an agent to pass the small scale test. We may have lost the direct connection between the small scale tests and how well they do in an actual real scale situation. So that's why we flipped the order on this. And it actually makes sense of it if you think about it on the way going forward. So as far as task one, which is our literature search, which is completed, we did a comprehensive literature review on a lot of different applications and uses, and we've identified approximately 30 potential candidates for testing. 12 of them are UL-listed fluorine-free foams. 9 of them have either British, European standard test approvals or ICAO type test approvals. 8 of them are wetting agents or encapsulating agents, and 3 or 4 SERDP ESTCP candidates which were specific compounds that were developed with SERDP ESTCP funding prior to this program itself. Let me see here. Most of these are all added with water the same way as you would with AFFF. So it's going to be a very high concentration of water with an additive to it. But all in all, it's going to be very interesting to see how this all plays out as far as capabilities are concerned. Now, all of the information we collected during task one, we actually have inputted into a giant spreadsheet with a row for each of these potential agents. And in that row, we have everything that's linked to test reports, approvals, MSDS sheets, SDS sheets, recommendations, things like that. So it's a very, very all-encompassing type data set to start this whole process with. And one of the problems that we're going to have kind of presenting this data going forward is that we're going to try to keep it as a blind study, because the federal government typically doesn't want to go on the record of endorsing some project, some product versus condemning another. So it's adding some headache on my end to try to keep all of this information sanitized without giving away exactly who the potential players are. The environmental analysis was also quickly done. It was done based on the chemical compositions as provided to us from the manufacturers. It was basically as a no-go, no-go type of an assessment, and they all kind of went through that first process pretty well. We're going to ultimately circle back and do life cycle assessments on ones that look very, very, very good as far as firefighting capabilities. Task 3 is our real scale fire test program. We're going to do 2 scenarios during task 3, a fixed discharge system, overhead sprinkling type system, and a manual firefighting type of a scenario. Both of those are going to be what I would refer to as kind of medium scale, but from the novice person, they would feel like large scale to you. They're typically, we're going to aim for about a 400 square foot pool fire. We're going to make these fires with representative fuels like JP5 or F76 to do our first screening, as opposed to like test fuels like heptane. We're actually going to use the real fuels to kind of put those fire sizes in perspective. So a 20 by 20 foot pool fire will give you a flame height of about 4 or 5 stories tall. So from a novice, that's a pretty big fire. And from those who are standing next to it, it would seem large as well. But so from an AFFF perspective, we're going to use AFFF, mil-spec AFFF, the baseline as a baseline comparison for all the agents we're testing during this program. So once we finish our first round of fire tests, which will be real scale, we're going to rank the capabilities, and we are going to down select some to go to smaller scale to try to develop the link between the small scale and the large scale. it's going to basically take a very, very poor performance to eliminate an agent from going back to small scale. During the small scale test, we're going to test the candidate agents against the 25 square foot pool and the 50 square foot pool fire that's included in the mil spec. We're going to start with 2 gallons a minute, which is the standard flow rate for the mil spec test. And we're going to increase the flow rate until we're able to pass that. So again, we're going to try to develop some kind of a link between the small scale capabilities as shown in the approval type size testing, using the mil spec as the basis, to the actual large scale testing that we conduct prior to that. At the end, we're going to document all of the tests that we've run, have a video database, as well as that large spreadsheet, which identifies all of the agents. Now, the NRL is going to be the keeper of the database, and we hope to grow that database as more technologies become available. We're going to bring in, as I mentioned earlier, some end users and some subject matter experts to try to chime in on what we think the capabilities should be for these foams, assuming that we're going to see significantly difference between the small scale performance and the large scale performance. But ultimately, we're going to have to decide going forward, whether it's now or somewhere down the road, if AFFF does indeed go away, how good is good enough. But again, I'm going to use a lot of these technical experts as kind of a backboard or a sounding board to figure out what makes the most sense as far as the path forward. So the ultimate benefit to DoD is a database on the capabilities of all the commercially available AFFF alternatives that we've identified to date. It's a logical first step. We'll have a link, hopefully, between the real scale and the approval scale tests again, because over the past 50 years when AFFF was originally developed, the mil spec now, that link has been blurred, if not completely lost the understanding of how well that actually links. And then ultimately going forward, we could indeed use this database and the information that we collect during some of the testing to develop a new mil spec for approving fluorine-free foams if we end up going that way. So as far as where we are in the program, we've completed tasks 1 and 2, the literature search and the environmental analysis. The real scale tests are scheduled for the spring. We'll rank the capabilities in the summer. Repeat the small scale tests or run the small scale tests in the fall, and hopefully complete the entire program by the end of the 2020 calendar year with a final kind of presentation, kind of documentation package completed in early 2021. So kind of as a high-level summary conclusion, so the use of fluorinated foams may be significantly restricted moving forward. Our understanding of the capabilities of fluorine-free foams needs to be developed. A database needs to be established as an ultimate first step. And that's kind of what we have proposed here, and that's our program to date. I need to acknowledge John Farley, a co-PI, principal investigator on this program. John works for the Naval Research Lab. He's the director of fire and test operations. He has 35 years of experience, about 20 years of owning the mil spec test and the QPL list for foams. And so John and I work on a daily basis to assess these. And as an interesting data point for you guys, the way I got into this business 35, 40 years ago was the fact that my next door neighbor, Jake Jablonski, invented AFFF. So that pretty much concludes my presentation, Rula.
Great. Thank you so much, Jerry. We've received a number of questions for you. The first one is from Marathon Petroleum, and it relates to compatibility of firefighting equipment with the fluorine-free alternatives. So are you going to consider compatibility with existing firefighting equipment to be part of the evaluation criteria and potentially approval for these fluorine-free alternatives? Because drop-in replacements can, is important to avoid expensive equipment change-out costs. Can you address that, please, Jerry?
That's a very good question. I'm glad you asked it. So our thought process is yes, we are going to work that into the logic process. We would prefer to be able to do something there is no really, at least from my knowledge right now, what I would refer to as a drop-in replacement for AFFF. However, if you can use the same proportioning systems at higher concentrations and potentially some of the same discharge devices, those types of things will be considered in ranking the capabilities of the foams going forward. As many of you may have heard already and know that fluorine-free foams rely solely on the foam blanket to put out the fire, and AFFF has both a film that's formed on the fuel surface to contain the vapor as well as the foam blanket. So discharge devices and foam quality is going to be key going forward. And I have to be honest with you, the hardware used by DoD today does not make very good foam quality, does not aspirate the foam very well. So it'll be an interesting progression going forward.
Thanks, Jerry. So Michelle talked about the TOP assay, or the total oxidizable precursor assay that was developed at UC Berkeley. Did you use the TOP assay or any other type of PFAS analytical methods to look into the fluorine-free foams and verify that they are actually fluorine-free? And this is a question from the Swedish Defense Material Administration.
That's a very good question. So the answer is not yet. The initial screening of the foams were based on information provided to us from the manufacturers and a review of MSDS sheets and SDS sheets that were included in that package, looking for obvious showstoppers. Ultimately, we're going to circle back after if we have some of them that look very good as far as fire performance capabilities, we will then go to detailed chemical assessments and life cycle assessments of those products.
Great, thank you. For those that are not familiar with the Navy MIL-SPEC, can you elaborate on what the exact requirements are in terms of getting to a fire and putting it out in terms of minutes and other criteria that you're going to be evaluating to try and meet that MIL-SPEC?
So right now I'm not trying to meet the MIL-SPEC. Okay, so that's a misnomer. So right now I'm going to assess the capabilities on a real scale, and then I'm going to go back and I'm going to run the two fire sizes in the MIL-SPEC at the 2 gallon a minute nozzle used in the MIL-SPEC to see how these perform. And assuming that they're going to fail, because we have tested a lot of them, a lot of the fluorine-free foams already, and none of them have passed the MIL-SPEC testing. We will then increase the flow rates until we get the right extinguishment times. And there's a number of tests in the MIL-SPEC between concentrations and fire sizes and application rates and extinguishment times. But in general, let's just say for conversation, they all need to be under a minute. Some of them have to be put out in 30 seconds. Some have to be put out in 45 seconds. So there are a number of parameters. So it's not really an easy test, an easy question to answer. But again, I'm not trying to have them meet the MIL-SPEC per the letter of the law. I'm just trying to see how they do against the MIL-SPEC test, so I can help develop a kind of relationship between the scaling, between the real scale and the MIL-SPEC type testing.
Great, thank you for that clarification, Jerry. Can you talk about whether the foams and agents that you're testing in your program, whether they're combined with water at low concentrations, like 3% or 6%, like AFFF is?
Yes, actually, so the ones, the foam concentrates that we've included in the program, the ones that have been through the UL 162 or the EN or the ICAO tests are all 3% concentrates, the same as the current industry standard for AFFF. So with the idea that, and kind of ties back to the first question, that maybe proportioning systems, we may be able to use current proportioning systems. So that played into some of those selections. A lot of those agents are available in like 6% concentrates and things like that, but we're focusing on the 3. Some of the encapsulating and gelling agents have varying concentrations and actually require their own special hardware. So all bets are off on those, because they're all over the place as far as how to proportion them and discharge them through devices.
Great, thank you. This is a question from the Colorado Department of Public Health and Environment. And what measures have you taken and planning to take moving forward to deal with the AFFF or the replacement discharges into the environment during or after, while cleaning up the waste after your testing?
So, so all waste is collected. We collect all the waste from any fire test that we run, and we hired a local waste disposal company. The one we use is called Clean Harbors. I'm located in Maryland. The Naval Research Lab is where we do a lot of our testing. They have a contract with Clean Harbors, so all of the waste is collected. We have liners on our concrete pads to basically be able to squeegee anything toward to collection points and basically put into containers to be hauled away. So that will be done. My understanding is, and of course this is Michelle's area, that incineration is the standard way for those types of organizations to get rid of these types of molecules today. So on a large scale. So that's how they're doing that. We have, from a firefighter perspective standpoint, all of our test personnel and firefighters all have PPE on to prevent any kind of contact between these agents and their skin, and any contact, they're immediately rinsed off and cleansed.
Great, thank you. This is a question from the Navy. Why is the large-scale test limited to 400 square feet? Is that a limitation of the test facility? Because the original mill spec large-scale test was around 1,000 square feet.
Yeah, so the world's become a lot more environmentally sensitive over the years since we did the original mill spec test 25 or 30 years ago and had the 1,200 square foot pool fire. I'd like to eventually go there, but we thought that the 400 was kind of an economical size. So it's kind of like more of an economic starting point, and it's very difficult to find a place to run those types 1,000 square foot pool fires. But I'm hoping that a follow-on program from this may actually allow us to go to those type of large sizes.
Thank you, Jerry. This is a question from Jackson Hole Airport. I'm not really sure if it's directly related to your presentation or your project, but it raises a really good point. Once you finish your project and you identify a menu of alternative foams, are you or someone being funded by SERDP and ESTCP, are they going to come up with some guidance to clean up the fluorinated foams out of fire truck tanks so they can be used with whatever those new foams are? Is this effort part of what you're doing, or are there any follow-on efforts that you're aware of?
That's a really good question, and that's a few years down the road. So I'm not the right person to answer that. I mean, we need to determine an acceptable alternative well before we figure out how to do the transition from the currently used foams to this alternative. So I'm sure there'll be a lot of environmentalist types and chemists involved in that kind of a transition and the collection and the proper disposal of it. But again, that's outside of my scope and outside of our window of time, I believe.
Well, thanks for taking a crack at it. Maybe one last question for you before we pull Michelle back in. And this is a question from the U.S. Department of Transportation from the Volpe Center. To what extent does your assessment consider the potential environmental and human health effects that may be associated with the fluorine-free foam?
So I have to admit, I'm kind of the fire guy experimentalist. We have an environmental group that are basically doing the chemical assessments and the life cycle type of assessments at the end of the program, as well as initial screening. So I don't know exactly what level they're going to be going into at that point, whether to try to get the crystal ball out to determine whether or not that there's any potential issues coming down the road. Because, I mean, as everyone on this call probably knows, we seem to learn environmental lessons the hard way. So, but it's a very good point. The guys that are working on that type of a project or working for me on that are very knowledgeable, and that they will do the best they can to try to make sure that there's something that's not going to sneak through other than to worry about fluorine as far as environmental hazards in the future.
Well, thank you, Jerry. We're all anxiously waiting to get the results of your work, and we thank you for your time. And stay on the line, because we do want to pull Michelle back into the discussion, but we'd like you to weigh in on some of the AFFF issues that are common to both of your projects. Michelle, let's start with you. And from a SERDP and ESTCP perspective, we discussed how SERDP likes to transition new technologies from the lab to the field. What, in your opinion, can be done to accelerate the availability of new approaches to treat PFAS-contaminated groundwater and other environmental media?
Thank you, Rula. So a couple of things. I think we need to have sites that are open to doing such demonstrations. And support for trying new things on site. I think that people are, sometimes a bit nervous about trying something new and untested on their sites, but that's the purpose of a demonstration, and not really waiting until something is deemed a standard practice before considering implementing it on site. That gets everybody involved. And not really just relying on the DoD to do all of the technology development and technology transfer. I guess that's sort of a big picture response to that question.
Thank you, Michelle. And Jerry, while we're talking about transitioning technologies, given that you're not going to be able to endorse any foams, you're going to be concluding that there are potential alternatives that can be used or not. How do you see how do you see your results getting transitioned to the end users that are working on identifying replacements and getting them in place? Do you have any recommendations on how that can be done quickly and efficiently?
Well, I think that the obvious answer is that, so the development of a new specification for approving fluorine-free foams is the first step. So what would happen is that we would develop a new spec, and then the manufacturers that we've already looked at, we would notify them and say, okay, we have some results that suggest that you may want to come in here and do these tests and get an approval for use. And then basically that would be published in the public domain to allow anybody that has a potential candidate to try to pass the new specification.
Great, thank you. And while we're with you, Jerry, are there obvious DoD applications where fluorine-free foams could be used today? Clearly, there's non-DoD applications, but specifically for DoD, are there any obvious applications for fluorine-free foams today?
Well, that's a real good question, Rula. So there are some applications where fluorine-free foams can be used today in DoD. I mean, when it's all said and done, you can compensate for poor performance of an agent by increasing the quantity of the agent. So, if you have a lot of flow rate, a lot of, discharge capabilities in a particular application, in theory, you could probably go to a lower performing agent and still be fine. The counter argument, of course, is that, first of all, DoD has always tried to stay as consistent or uniform throughout all of their facilities and all of their applications to use the same types of foams. They also like to be, there's a compatibility issue that DoD likes, that they like to be able to have a couple candidates all be able to be interchangeable. so that they don't get stuck into, sole source, as opposed to competitive bids. So they're from a performance perspective, I think that there are some applications, but from a practicality and the mindset of the DoD, it's going to be hard to get there without changing the mindset about we want to stay uniform, we want to be compatible with other agents that we're using and things like that. There'll always be hurdles.
Thank you so much, Jerry. And one last question for Michelle before we wrap up. Michelle, in your opinion, what have we learned from our history of treating other contaminants in soil and groundwater at sites over the years that will help us address the whole issue of PFAS?
Thank you, Rula. So I think we need to keep in mind the physical characteristics of the system. We spent a lot of time learning how important the subsurface characteristics, the media properties, the heterogeneity, and so forth are in developing treatment systems. Now that we're transferring to contaminants that are more difficult and recalcitrant to treat, one thing we need to keep in mind are those lessons that we have learned about the subsurface when we are trying to work on new approaches to get these PFAS contaminants. So we don't want to go all the way back to the beginning in treating PFAS. We want to kind of adopt all of those lessons learned along the way.
Great. Thank you, Michelle. And thank you, Jerry, for a fascinating webinar. Again, if our audience members would like additional information, we'd encourage you to download a copy of the PDF of their slides, of our speaker slides, and following the links provided there for the detailed information from their project. Our next webinar is on Thursday, October 24th, and it will focus on results from DoD-funded research on addressing difficult-to-treat contaminated sites with high-resolution site characterization and contaminant mass flux reduction. This webinar will also feature two speakers, Dr. Chin Man-Mok and Ms. Poonam Kulkarni, both from GSI. Registration is open for this webinar, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. And as I mentioned earlier, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you'd like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your time.